Okay, so we've talked about polar bonds and nonpolar bonds and ionic bonds. And now we're going to talk about the entire molecule. If you have a diatomic molecule, there's only one bond, and so things are pretty simple. If the bond is polar, then the molecule is polar. So the example here is hydrogen chloride. And what I want you to know is that you have two nonmetals and they are not the same. So I expect you to predict that this is a polar bond. You can verify that by comparing electronegativity differences, but most of the time that's not necessary. So we can indicate the polarity of this bond, writing a net dipole moment as an arrow pointing to the more electronegative element, and then a little plus sign over here. This indicates that this chlorine, which is more electronegative, is hogging the electrons. And so we have a partial negative charge here and a partial positive charge there. In a polyatomic molecule, the polarity of the molecule depends on the geometry, because now we have multiple dipole moments pointing in different directions, and sometimes they'll add up, they'll constructively add, and other times they will cancel each other out. So you can have polar bonds and a nonpolar molecule. So let's look at carbon dioxide. Carbon dioxide has two polar bonds. So we've got this carbon-oxygen double bond. Oxygen is more polar, and so the electron density is pulled towards the oxygen. And over here, the electron density is also pulled to the oxygen. But the molecule is linear, and so those bonds are essentially opposing each other. The dipole moments go in opposite directions, 180 degrees, and so the molecule is nonpolar. There isn't one end that's more positive than the other. So if we draw the electron density, we see that it's symmetrical. Does anybody have any questions about that? Yeah, we're going deeper today. Like it or not.
So nonpolar also can occur. Well, they're not. So between carbon and oxygen, it's not polar. Or no, it's not nonpolar, right?
Right. The bond between carbon and oxygen is a polar bond, but there's two polar bonds, and they're pulling the electrons in opposite directions. So overall, it's nonpolar molecule. Yeah. And so dipole moments are vector quantities. If you're, a math type person, remember what a vector is. A vector is something that has magnitude. It has size, but it also has direction. So we often represent them as arrows. So dipole moments have directions and magnitudes. And so if the magnitudes are equal but going in opposite directions, they cancel each other out. They add to zero. So for these dipole moments, the direction points to the more electronegative atom, and the magnitude is going to be proportional to the electronegativity difference between bonding atoms. So we're mostly going to be concerned about the direction of these dipole moments, and we're going to be very, very not concerned about the magnitude of them. So in water, we look at these oxygen-hydrogen bonds. Oxygen and hydrogen are different nonmetals. This is a polar bond. Oxygen is more electronegative, and so the dipole moment points towards the oxygen, with the hydrogen end of this bond being more positive. But the shape of water is bent. It's not linear like carbon dioxide because there are two lone pairs on here, and 4 electron groups make a tetrahedral molecule. That's the electron geometry. 2 of those are lone pairs, though, so the name of the structure, the molecule, let's just start over. The name of the molecular geometry is bent, right? So this is a 2-dimensional molecule, so we can lay it flat in the plane of the board or the screen. And we have a vector going this way, and we have a vector going that way. And they're going to add together and give us a net vector going this way. So vector addition can be a bit confusing. It can help if you think about playing tug of war, right? So if we go back to carbon dioxide, here we've got a person in the middle, and they're holding on to 2 ropes. So each dipole moment is a rope going between two people. So here's carbon. Carbon's holding on to two ropes. Oxygen's pulling on one side. Another oxygen's pulling on the other side. They are equally strong, and they're going exactly opposite. And so this group of people playing tug-of-war isn't going to move, right? This person in the middle is going to feel like their arms are getting pulled off, but there's not going to be all of them moving to the side. Does that make sense? If we think about a similar situation with oxygen, and here maybe oxygen is the dad, and he's playing tug-of-war with two little boys, his sons perhaps, and the one boy's pulling off in this direction, and the other boy's pulling in this direction, but dad's stronger. And so dad's opposing both of them, and the whole shooting match is going to go this way, right? Dad's going to pull backwards, and they're pulling off at angles, but they're going to have to come with him because he's stronger. Does that make sense? If this was a linear molecule, that wouldn't happen. If we had oxygen in the middle and hydrogen here, it would be a nonpolar molecule because they would oppose each other and nothing would move. The dipole moments, the vectors here, add to 0. Here the vectors do not add to 0. We're not going to care how much it adds. You know, does it add to 5 or 2 or what? We don't care. It's just not 0. If it's not 0, it's a polar molecule. Any questions so far?
It's not 0 if it's not linear.
Well, it's a little more complicated than that. Yeah. So this one, because it's linear, we have two dipole moments. They're going to be opposing each other. Then it will be linear. This one with two dipole moments is going to be bent, and so it does have a dipole moment. But then things get a little more complicated when you have 3, 4, 5, or 6 dipole moments. Yeah. So in determining polarity, we first draw the Lewis structure and identify the molecular geometry. That's what we covered last week. Then we're going to identify, does the molecule have polar bonds? If all the bonds are nonpolar, the molecule has to be nonpolar because all the vectors are 0. And so it doesn't matter what direction they would be going, they're just all 0. So you can only have a polar molecule if you have polar bonds. Okay? So then we would look at the polar bonds as vectors pointing towards the more electronegative atom with the length proportional to the change in the electronegativity, or the difference. And then we determine, do those polar bonds add together to form a net dipole moment? If they sum to 0, the molecule is nonpolar. If there's a net vector, the molecule is polar. Now this is the more rigorous explanation set of instructions. I do have a shortcut that is easier to apply. I can't remember where it's coming in the slides, but it's coming. So let's do this problem. A molecule contains 3 identical polar bonds in a trigonal planar molecular geometry. Is the molecule polar? It can be helpful to draw, right? So there's a molecule with 3 polar bonds, trigonal planar. So here's my central molecule, and I have a polar bond coming up here. I don't know why that's kind of squished. Trigonal planar. It's making a triangle, right? So let's just imagine that the more electronegative element's on the outside, and so the vectors would be pointing along this way. So there's one vector, one dipole moment. See how the dipole moments are all pulling out from the central atom? The bonds are identical, meaning the length of these vectors is the same, and they're pulling in 3 equally spaced out directions. If you're playing tug of war like this, is this guy in the middle going to move at all? No, because somebody's pulling this way, somebody's pulling this way, and somebody's pulling that way, and it's like I'm being pulled literally in 3 directions, but they're all equally strong, and so I'm not going anywhere, right? I'm just standing still. So is this molecule polar? No, it's not polar.
Because it would need to be unequal, right? It would need to-
Yeah, if you have this trigonal planar molecular geometry where things are spread out, equally spaced, then you'd have to have one of these being a larger vector, larger dipole moment, in order for there to be a net dipole moment in the molecule. Or you would have to have these be unevenly spaced, right? But they're not. They're spread out equally. Any questions? This is going to be a bit hazy until we get through all of it, and hopefully it'll make more sense. So a quick review of vector addition, right? So vector addition in one dimension is like adding numbers, adding positive numbers and negative numbers, right? It's like a number line. So here if we have +5 and +5, these are equal in length, equal in magnitude. They're both going in the same direction. They're both going the positive end of the number line, right? So 5 and 5 gives us 10. Here we've got a -5 going off on the negative end of the number line and a +10 going to the right. So when we add these vectors, we get 5 positive. Does that make sense? Because these are going in opposite directions, but the positive wins because the positive is bigger, right? Here we have equal in magnitude, opposite in direction. So -5 and +5, and these add up to 0. They cancel exactly. Does that make sense? We have to understand the one dimension before we go into 2 and 3 dimensions. So if you have any questions, ask them now. In 2 or more dimensions, what we're going to do is we're going to draw a parallelogram. So here we've got this vector A and this vector B. And to identify what the sum of them is, we're going to draw a parallelogram. So here along B, we're going to draw a line that's parallel to that and the same length, starting at the end of A. And then for A, we're going to make a parallel line over here from the end of B up to this point here. So you make a parallelogram. And the sum of these is from the starting point here to where those other lines intersect. So here we've got this one going off in that direction, this one going off in that direction, and they're going to add together. If you imagine someone, if you imagine this is a tug-of-war game, and here you've got, somebody standing here, and there's somebody on a rope over here, and somebody with the rope over here. And this person is pulling this way, and this person is pulling that way. Overall, the 3 people and their ropes are going to move in that direction. Does that make sense? Kind of, a little bit. So this guy keeps pulling in this direction, even as they're moving. And this guy keeps pulling in this direction, even as they're moving. And so because this guy's a bit stronger, instead of going straight up the middle here, it's going to veer off to this side a little bit because this one is stronger. This vector is longer. Well, we draw them longer because that indicates the magnitude of the vector. For the bonds, it's the difference in electronegativity. And like I said, most of the time we're not going to be worried about is one larger in magnitude than the other. We're mostly concerned with the directions. 3 dimensions, you have to do this, 3 vectors, you have to do them 2 at a time. So you take A and B, and you add those, and you get R. And then you add R to C, and you get R prime. Same thing for this one. Now this is like that example in the conceptual connection where we had a trigonal planar molecule and equal vectors. So here A and B and C are equal in length, and they're going in opposite directions as a triangle, right? So if we add A and B together, we'll get R. And this R and that C are exactly opposite of each other. And so these vectors cancel, and there's no dipole moment for the molecule. These A, B, C add up to 0.
So why do you have to do an arc line with A, B, and C?
Well, because you can't add three vectors at once. We can look at this and say, oh yeah, that's symmetrical and they're all equal and they're going to cancel each other out, but you can't actually add them together like that. The good news is you don't have to understand vector addition. It'd be good if you do, but it's not necessary. So this is giving some common cases of adding dipole moments with molecules. So here if we have a linear molecule and the dipole moments, we have 2 identical polar bonds, then they're going to cancel each other out. Here, if we have a bent molecule, like in water, we have 2 identical polar bonds, but they're not exactly opposing each other, like this one. And so the sum of them is going to give this little red arrow, and that's the dipole moment for the molecule. Here we have trigonal planar with identical bonds. We've looked at that a couple of times now. That cancels out. That's 0. Tetrahedral, 4 identical bonds. Same idea, but in 3-dimensional space instead of 2-dimensional space. Those are going to cancel each other out. In a trigonal pyramid molecule, here we have 3 bonds, and the dipole moments are pointing sort of downward towards those atoms. There's probably a lone pair up here. And so when we add these together, we have this red arrow. We have a net dipole moment.
So what exactly is this something that we just need to memorize?
Well,
Because
right now you just need to bear with me. Okay, we're still coming up to my shortcut. And once we get to that, then if things still don't make sense, then we need to figure it out. Oh, here's my shortcut. This works like 95% of the time, which is pretty good. And you don't have to think about vectors. So make a note of this. So a molecule is nonpolar if both of these things are true. There are no lone pairs on the central atom, and all the atoms bonded to the central atom are the same or have the same electronegativity. The same atoms or the same electronegativity is important because that's going to determine the magnitude of the vectors. So when number 2 is true, that means all the vectors have the same magnitude. Number 1 is important because if you have lone pairs on the central atom, that's where things are going to be asymmetrical. If there are no lone pairs, those bonds are spread out evenly in space, and they will add to 0. So 2 conditions: no lone pairs on the central atom, lone pairs on anything else don't matter at all. And all those bonds need to be either the same or have the same magnitude, same electronegativity difference. So let's use that and look at this question. Yeah, it's a great way to treat the pencil. Drop it in the floor. Determine if CF4 is polar. We have to draw the Lewis structure and determine the shape first. Okay? So if you're rusty on that sort of stuff, we need to review that. So here we've got carbon and 4 fluorines. So we'll start out by putting the fluorines around like that. And then we would look at the number of valence electrons and fill those in. And the point here is not to teach Lewis structures, so I'm going kind of quickly for that. So there's our Lewis structure. Then we need to identify the shape of the molecule. Well, according to the more rigorous method. Let's try my shortcut method first. Are there any lone pairs on this carbon? No. Are all of the atoms bonded to the carbon the same? Yeah. So the magnitude of these dipole moments is all the same, and they're spread out equally. They're going to add to 0. This is nonpolar. That's the shortcut method. If we have 4 electron groups around the central atom, what's the electron geometry? Tetrahedral, right? So tetrahedral is going to be shaped like that. And then we would look at the vectors. Let's try this. So I can be too fat. So who's more electronegative, fluorine or carbon? Fluorine. So this would be a vector going towards fluorine, and this is a vector going towards fluorine, and this is going back towards that fluorine, and this one's coming out towards that fluorine. In a tetrahedral molecule, those bonds are going out in 3-dimensional space, spaced out equally from each other, right? And just like in the linear molecule, where you have 2 bonds spaced equally, they're going to cancel each other out. In a trigonal planar, when you have 3 bonds spaced equally, they're going to cancel each other out. Here, 4 of these vectors spaced equally are going to cancel each other out. Anybody have any questions about that? What if I made this fluorine, no, not that one. I'm going to take this one out. What if I made this fluorine an iodine? What would happen to this vector? It'd be smaller, right? Because iodine is a lot less electronegative. And so, let's see if I can draw this. So now we've got just a smaller one here. Does that show up? Instead of the big red one. So if I'm adding this green one and these 3 red ones that are larger, do you see how that's not going to cancel out? It's not symmetrical anymore. Nonpolar molecules are symmetrical. The bonds are spaced equally, and the atoms that they're bonded to are the same, or they have the same electronegativity. So this would be polar. Any questions? The polarity of molecules has a big effect on the properties of the compound. So here we have an illustration of 2 water molecules. In the water molecule, we have dipole moment, as you can kind of see that. For each of these pointing towards the oxygen. There are lone pairs on the oxygen, which is why this is bent. So there's lone pairs. It's a polar molecule. What the lone pairs do is they make it not symmetrical anymore. So we have these polar molecules, and they'll have a negative end. It's just a little bit negative. It's not an ion. And they'll have a positive end. The positive end of one molecule is attracted to the negative end of the next molecule. And this causes them to kind of stick together. They are going to be more attracted to each other than if they were not polar and had none of these electrical charges, right? It's like magnets. The south pole of one magnet is attracted to the north pole of another magnet, and they will stick together. So we all know that oil and water don't mix. This is the reason. The water here is polar. all of these molecules are very attracted to each other and they're going to stick together. Oil is nonpolar and it doesn't have those dipole moments that can cause it to be attracted to other oil molecules or to water molecules. And so the oil gets pushed out because the water likes itself so much. It's a little bit like mixing magnetic marbles with regular glass marbles. The magnetic marbles are attracted to each other. You can imagine how this would happen. They're going to clump together, and the glass marbles are just going to get squeezed out. Your question?
Is that for all oils?
That's for all oils, yeah. Well, some oils, you could have an oil that's more dense than water and would sink. That could be possible. So it would be on the bottom, but yeah, oil and water, they're not going to mix. So any other questions? Water is polar because it has a bent molecular shape, and so the dipole moments of the bonds don't add up to zero. Yeah. So if we were looking at net dipole moment, it would be like this. Well, no, that's a good question. How do I know it has a bent shape? Because I know what its Lewis structure looks like. It has lone pairs. Yeah. That's what makes it bent and polar. It's not symmetrical. It's symmetrical, but the vectors don't add to zero. Because if we just see HOH, we're like, well, why isn't that linear? You know, it should be linear. But there's two lone pairs. And the lone pairs force these two bonds to be closer to each other than we would expect. They're actually 104.5 degrees apart. Definitely not 180 like this. So because of the molecular shape with the polar bonds, water is a polar molecule. And it's a good thing it is, because otherwise life as we know it would not exist.
So really, it would be beneficial to draw the lone pairs not symmetrical almost? Because like right now it looks symmetrical, right?
Right.
The lone pairs are symmetrical.
So what's nice about Lewis structures is that they fit, for the most part, they fit very nicely into a two-dimensional realm, like, you know, the screen or a piece of paper. And it's fine to draw them like this. But we either have to draw them funky or recognize that what we're actually looking at is we're looking at something like this, where we've got a lone pair here and another lone pair back there. There are four groups. It's a tetrahedral electron geometry, but then the molecular shape is bent. So this is why my shortcut rules are really nice, because you actually don't have to go this far. You can look at the Lewis structure. Lone pairs, oxygen, hydrogen, they're not the same polar molecule. Okay? Any other questions? I'm not going to test you on this, but I think it's interesting and applies to real life. How does soap work? I think we all recognize that, you know, if you've been greasing a pan with Crisco or you've got butter all over your fingers, you can't just rinse it off with water, right? If you've got sticky candy on your hands, you can just rinse it off with water. It comes off just fine. But oils like butter and Crisco do not, because the water's polar, the grease is nonpolar. They don't mix together because the water is just so attracted to the other water molecules and won't let the grease in. So what soap does is it sort of acts as an intermediate, and this is a representation of a soap molecule. So we have this long carbon chain here. This is all carbon bonds in the middle with each other, and then hydrogens. Now, carbon and hydrogen is the one pair of nonmetals that I said I want you to remember. Those are nonpolar bonds. So all of these bonds down here are nonpolar. Up here, we have a polar head. We've got a carbon and two oxygens here. The oxygen-carbon bonds are polar, and this whole molecule is not symmetrical. And so this end is polar, and the rest of it is nonpolar. So what happens is this nonpolar end will get into and mingle with the grease or the oil molecules, and the polar end will be attracted to the water molecules. Let's try it this. Well, let's see. I'm trying to decide how to draw this. So here's the polar end, and what's going to happen is the soap molecules, I'm drawing this in 2 dimensions, but it's actually occurring in 3 dimensions. So here in the middle is our grease. And so the nonpolar ends of the soap molecules will get in there and mix with the grease. The polar ends don't like the grease, and so they're like, I'm going to stay out of there. They're going to surround it a little bit like, the old days, they're circling the wagons to defend, against marauders. Circle the wagons. So we're protecting the grease in here, and then we've got this polar head on the outside, and this is going to make a small micelle, a little globule, very, very small. And then because it's polar on the outside, the water's like, oh yeah, hey, come on right through. And it will mix, and so you can break the grease into little tiny pieces that will wash away with the water instead of them just sticking to your skin. Any questions? That's what soap does.